All right, lesson 1-4 we're starting today. Just as a general reminder, each lesson we have 4 things that we're going to go over. And so from your digital classroom, if you go to chapter 1, we are doing lessons 1-4. So you'd scroll down to your 1-4. The 4 things we're going to look at today is you must take attendance. Your link is listed in the PowerSchool Learning site right here. Number 1, whoops. Put it on the wrong spot. There we go, right there. Here's your 1-4 link. We're going to watch the YouTube videos, take notes on that. Number 3, you'll take exam 1-4, and number 4, you'll have an Alex assignment. Both of these 2 things will be due Thursday of next week. Due Thursday of next week. At 11:59 p.m. So those are the 4 things. Now, just a little recommendation. When you're going to watch those videos, what I would recommend you do is to have the completed packet open. So I'm going to click here for the YouTube playlist. I'm going to act like if I were you, a student, and these are the sets of videos that we'd watch, which I'm doing this lesson introduction right now. But as you start watching those videos, I would, if I were you, have a copy of the completed lesson packet open as well. And so that whenever you finish example 1's video, it's going to take you through this slide and this slide, and it's going to stop right here. The video is not going to teach you how to do this. But what I would recommend is while you're watching that video, to immediately pause, flip from YouTube screen over to this complete lesson and try to work the problem while it's fresh in your mind how to do it. Write down your answer somewhere and recognize that when you take the lesson exam, these get randomized. So A won't necessarily be A, B will not necessarily be B. These will be randomized. So find your answer and write down what the answer is, not the letter. And then go back over and watch example 2. And when you watch example 2's video, I'm going to write out all of this and I'll solve this problem. And then I'll leave you at this problem here. So you would, after you watch this video, as example 2, you'd come over to their notes, you'll scroll down to this slide, work number 2, and get your answers. Once you do that, you'll come back and submit them in to here. That's just my recommendation. And one more thing, just again, if you're struggling with how to get into Zoom you're on your phone and you don't want to be on your phone, what you can do is I've submitted this video right here. Follow all the steps in this video. If you click that under the Zoom links on the home page, the 2020-2021 page, please follow all these steps in this video to solve your issues. If you're having errors with signing in, if it keeps asking for a proxy or something like that, if you watch that YouTube video, I will work you through all the steps so that you can start watching live on your Chromebooks. So with that, let's get going on 1-4. I'm going to walk you through. This is not what I want. This is not what I want. I want this over there and this over here. Okay, we're going to look at these 3 problems. And to help us out, what I've done is I have taken these graphs and I have graphed them on Desmos. I like Desmos. It's a free website. And so for you, if you want to see what I'm actually looking at, I got a QR code right here. If you have your phone available, you can scan that Desmos QR code and it'll load up this page right here I'm looking at. And so I want to look at number 1 here. It says find the end behavior of this problem. And so end behavior, if you want me to write this a little bit more in detail, what end behavior is talking about is what's the graph doing on the far left and far right. Far left and far right. That's what we're trying to determine what's happening. So I'm going to come over here to my graph, specifically this Desmos graph over here, and we're going to talk about when the graph goes farthest to the left and when it goes farthest to the right, what's happening to the y values. Because the way you write your answers here are in limits. And so last lesson I taught that whenever you see these symbols here, the way I want you to interpret this is what happens to y as x approaches negative infinity. Or if I translated it, what happens to y as x approaches the left end of the graph. And so on this picture, as we look, what is happening as we go left? As this graph goes further and further left, what's happening? what's happening as we move further and further left, as these x values get smaller and smaller as they approach negative infinity, what happens to the y's is the y's are getting larger and larger. This is my y-axis, they're getting larger and larger as my x-axis gets smaller and smaller. So as x approaches negative infinity, meaning as the graph goes further and further left, my y's are getting larger and larger. They're approaching positive infinity. And so if this were your question here, like if you were given this limit, and maybe this was a fill-in-the-blank question on Alex, or it might be a multiple choice on the lesson quiz, what you would do is you'd be looking for the answer that has x going to negative infinity while y goes to positive infinity. That would be your answer for the left end behavior. That's the left end behavior. That's what happens when we go left. So now let's check the right end behavior. So if I were looking for the right end behavior, this problem would be changed, and I would have a positive infinity right there. And so now you're saying, what's happening to the y's? F of x means y, represents the y, as x approaches positive infinity or the right. So on my x-axis, as we go further and further to the right, and while x is getting bigger and bigger, what is happening to my y values here? As we go further and further to the right, and x is approaching positive infinity, what's happening to the y values? What are they approaching?
Positive infinity.
So I'm hearing positive and negative infinity. So let's think about this. What's happening? The graph is moving which way, up or down?
Down, it's decreasing to negative.
Decreasing. So it'd be decreasing to negative infinity. And so if this were your problem, you'd be either looking for, if it's a multiple choice, f of x approaching negative infinity, or if it were fill in the blank, you would type in that symbol, negative infinity. And that would be the answer to number 1. Now, I know for many students, this could be confusing if I just left it here. So I'm going to give some extra examples. I just gave you your answers. Now I'm going to do some extra. And so in the videos, I talked about each piece of the graph. For pre-cal's sake, we're going to talk about 2 limits per piece. So like this piece right here has 2 limits that we would talk about. And this piece also has 2 limits. So I have 2 of them written up here in blue. And I wrote with these symbols. Now we're going to look at the other 2. We're going to look at this limit as the graph goes this way. And we're going to look at this limit. So each piece has 2. It's at the ends of the graph, if you will, of each piece. So we're going to talk about those 2 limits. So on this limit here, I want to touch my graph. What I like about Desmos is if you're using a computer, you just click with your mouse and you can click on the graph and it shows you the points. So you can see that point as I shift it up with my mouse is changing. Or if you're on a cell phone, you just simply touch your screen and it gives you that same point. So it appears that my x's are getting closer and closer and closer to the number 7. The x's. I'm only looking at the x values. So I'm only looking at the x values right here. I have to just kind of click that to make it freeze. So the x's are getting closer and closer to 7 as they go off the screen. Now, how do I know it's also 7 is I can click this piece and you can see that the x's are getting smaller and smaller as they approach the number 7. This graph is a function, so this piece cannot cross over on top of this piece, but they're going to approach the same number. As this graph gets closer to a 7 for the x, this graph approaches 7 on the x as well. And so the way this would show up, if you were, I don't know how to make that go away. That is not what I wanted to do though. I had just totally messed up everything. Sorry about that. Okay. If we were going to write these on homework, the way they would show up on the homework is you would see it and they would have a 7 written on the limit. It would have LM f of x equals x arrow with a 7, and this one also would have a 7, but there's one difference. This limit would be represented with a 7 with a plus symbol up where the power would normally be. This one would have a negative, and all that's saying is you're looking at the piece on the left side of 7. So it looks like these are counting by 2. So if this is an x value of 7 here, this with an x with a 7 minus, that means look to the left of 7. You're looking at this piece. I'm looking at this piece, not this piece. This is the plus piece. That's the plus piece. This is the minus piece. That looks like a -0. Let me put it up above. There you go. This is the minus piece. This is the plus piece. So on this graph, what's happening to this graph as it gets closer and closer to 7? Which way is the y's moving? Which way are these y's moving?
On which graph?
On this piece as we go on the right side of this piece right here. So I'm looking at the left piece, the one that's above the x-axis. What's happening as it's moving upward? Oh, I just gave you the answer. I meant what's happening on the right side of that piece? It's moving up. And so this one's answer would be a positive infinity because this piece is moving up. Just like this piece was moving up, this piece is also moving up. What about over here? What's happening to this piece? As this x approaches 7, the y is approaching, I think I heard it down. Yeah, negative infinity. And so that would be the answer for this limit. Okay. I'm going to throw in a little extra. What you're going to learn about this lesson on 1.4, the thing's called Extrema. They're talking about maximums and minimums. This graph, I see 2 extrema. This is an extrema. It's a local maximum because it's like the top of a hill. So that point would be called a local max. And somewhere in here, I'll just put it right there, we would have a minimum because it's the bottom of like a valley. Okay, so you have a minimum in here, you have a maximum right there. That's what you're gonna learn about in this lesson, but the limits are a review of last lesson. So all in all, the answer to this problem, the end behavior is talking about the left and the right. It would be talking about the blue parts. As we go to negative infinity, the graph goes up. As we go to positive infinity, the graph went down. Okay. Now, I said a lot. Let's now look at number 2. Let's determine whether this second problem is continuous at 4. So to do that, I'm going to clear my ink here, and I'm going to pull up the second graph. My second graph is this graph. We're going to look at this one, but I need to go. There we go. I'm going to zoom in. Oh, not that far. Let's do it like this. There we go. It asks, determine whether this function is continuous at 4. So at the x-at value of 4, does this graph, are these graph, let me ask you this way. Is this one piece or 2 pieces of graph?
2.
2 pieces. So it's not continuous. It fails what I'll call the eye test. Eye being like your eyeball. It fails the eyeball test. I see 2 pieces. It's not continuous. That means it's a break. Now, if it's a break, there are 3 types of breaks. 3 types of discontinuities. 3 types of discontinuities. I'm going to just say disc, because there's the word right there. They are an infinite break. That's where it breaks and goes to infinity. A removable. That's when you get an open circle. Or a jump, and that's just where one piece seems to move somewhere else, but it's not going to infinity. So those are the 3 types of break. When we look at this one, we're looking specifically at the value of x equals 4. So that's right here. This is where x equals 4. What's the graph doing on this break? Where is this piece heading? Right here, the left side. Where's that piece heading?
It's going down, negative.
That's right. As x approaches 4 here, the y's go down to negative infinity. And I'm going to put on the minus. That just means it's the left piece I'm looking at. I'm looking at this piece. And over here, as x approaches 4 on the right piece, so I'll just label this the right piece, what's happening to the y's?
Going up.
They're going up to infinity. So notice one side's going up to infinity, the other side's going down to negative infinity. Since they're going to infinities, you would say this problem has infinite discontinuity for number 2 at x equals 4. And this would be our answer here for number 2. It's an infinite discontinuity. So wait, why isn't it infinite discontinuity? what about the picture told us it's infinite?
They're going both infinite on x equals, I mean on 4.
That's right. So let me show you real quick so what it could look like if it were removable. So I'm done with number 2, and I'm going to now change it. So I'm going to clear the sink, and I'll show you. Here's what removable would look like. Removable, I need to edit my equation, will look something like this, which at first, a removable seems to pass what I call the eyeball test. It looks like this is one piece. Would you agree? This looks like it's one piece of graph.
Yes.
But when I go to x equals 4, I'm going to zoom in for a second, where x equals 4, that's too far in, can't get it. I'm going to highlight the graph right there, and when I get to 4, look what it does to my circle. Can you see what is my circle there on the line? Is it an open circle or closed circle?
Open.
Open.
It's open, and it says on the y value it's undefined. That's what a removable looks like. A removable is an open circle at the value. So infinite, the graph broke and went to infinities. Removable, it just looks like an open circle. And to show you a jump, so that would be removable, what I just did there. This was infinite. A jump would look like this one. You see how there's a gap in the graph? So it fails the eyeball test. A jump will fail the eyeball test. You can tell it's two pieces, but the graph does not go to infinities. They just jump from one place to another. That's what jump is. So infinite, graph goes to infinities, fails the eyeball test. Jump fails the eyeball test, but they do not go to infinities at the break. Removable passes what I call the eyeball test. It looks good at first until you highlight the value, and then you find out it's actually undefined and it has an open circle. So that's kind of the difference there on the 3. Algebraically speaking, if you want to know the algebra, the way you have a removable, I don't know if you noticed what I just did to this equation. A removable occurs whenever a factor in the top gets simplified or canceled with the factor in the bottom. Whenever you can remove a factor, it becomes removable. So since what I did is I added x minus 4 to the problem. Notice it doesn't have x minus 4 up top. When I added that, what the calculator does, without showing us, is it removes that portion. Since it removed it, it became a removable discontinuity. So that's the algebra. An infinite is something in the denominator, a factor in the denominator that does not get removed. So like this one, it could not cancel, so it was infinite. And a jump occurs on piecewise whenever the numbers don't match up, like whenever there's a gap in the numbers. So let's do number 3 to find out if it's a jump. To find out number 3 is a jump, you first notice the x value is 2 on this number 3. So we're looking now at x value of 2, and I'll pull up the graph in a sec. I'll pull up the graph right now. Number 3, it's right there. To find out if it's a jump algebraically, you plug in the numbers into the graphs. This is called piecewise. So if I plug in a 2 here, it's saying 2 plus 6. Well, what is 2 plus 6? If you plug in an x of 2, 2 plus 6 is
8.
8. And then you plug in a 2 here. What's 2 squared?
4.
4. So 4 plus 4 is also 8. You see how those are the same numbers? Because they're the same numbers, this is not a jump. It would be continuous. It passes the eyeball test, and these two pieces connect perfectly. You see how they connect right there at the y value of 8? X is 2, the y value is 8. That's because, oops, sorry about that. That's because they connect. So something's a jump if one of them were a different number. What I'll do is I'll change this equation to be x squared plus 6. Because then 2 squared is 4, 4 plus 6 will give us 10. You'll see there's a break. So I'm going to change this to where it says x squared plus 6. And jump looks like this. You see how there's a gap in the graph now? It's because algebraically these numbers did not equal each other. So that's how you get a jump. But let's do the problem because I didn't write the answer down. Here was the original problem. According to the original problem, does this look like one piece or two piece? Does it pass the eyeball test or does it fail? What do you see?
It passes.
It passes. Passes the eyeball test, and if you want to do your algebra, you plug in the numbers, and since they're the same, it's continuous. So number 3 is continuous. And that would be your answer on number 3. Okay, I flew through that bell ringer. What I'm going to do now is I'm going to give you some extra examples that we're going to talk through, and you're going to tell me what the value is. First off, for today's lesson, what are you going to call that point right there? What's the name of the bottom of a valley? If you see a valley on a graph, what do you call that?
Negative max.
Not a negative max.
No, isn't it called the minimum or something?
Minimum. That's a minimum. And you'll learn specifically if it's the lowest on the entire graph, they'll call it a absolute minimum, which that one is. Okay. Now let's see, I'm gonna pull up this graph. Whoops. I'm sorry, let me refresh because I want to get my window zoomed right. I'm gonna pull up this graph, and I want you to tell me, what is the answer to this? If you're watching on a video, not live, but if you're watching your own, just pause the video so you can think through what the answer is. What would be the answer to this question? All right, let's check what the answer is. I'm going to call this piece number 1, piece number 2, piece number 3, piece number 4. Now I have a student live who knows the answer. They said the answer to this is negative infinity. Now where did you look to get that answer? Did you look at 1, 2, 3, or 4 to get your answer there?
Well, I looked at 2.
You looked at 2.
I don't know if it was right, but I looked at 2.
Well, you got lucky.
Yeah.
This is going down to negative infinity. The problem is x here isn't going to negative infinity. This x, let me touch the graph and find out for sure. It looks like it's getting closer and closer to the value of 7. So this x is approaching 7, and since it's on, I should have looked at it here. That's the x value of 7. Since it's on the left side of the graph, it would have a 7 minus. So you got lucky. That is the right answer, but you should have been looking right there. That's where x is going left to negative infinity, and the y is going to negative infinity. So now I'm going to ask another question. Let's see. I'm trying to decide what I want to do. Let's do this one. What if you had to find this? I'll let you think. If you're watching the video, just pause it. Think through what you think the answer would be. Again. All right, so the answer here is positive infinity, but the 7 plus, what you need to do if it's a 7 on the x is you go to the x value of 7, and the plus means it's the right side. So I'm not looking at this piece, I'm looking at this piece here. And so here's the 7. At the 7, this graph is going up. That's what the y's are doing, they're going up. So as x approaches 7 on the positive side, or the right side of 7, the y's are going up. And so the very last limit here would be this piece 4. And so the way it would be written is since the x's are moving to the right, this is going further and further right, the x would approach infinity and the y's would also approach infinity. So let's take another look at a different problem. By the way, you would call this point right here a minimum, and somewhere in here you would have your maximum. Wherever the highest point of this hill is, you'd have a maximum. They all look pretty close. But if I zoomed in, somewhere I would actually find, let me clear my ink, somewhere in there I'd actually find a maximum point. But I'd have to keep zooming in. All right, we're going to change and now look at this piece. Okay, this time, check out this graph. This graph, how many pieces do you see?
3.
3.
Yeah, there's 3 pieces. So because there's 3 pieces, there could be 6 limits. Each piece can have 2 limits. So I could have a limit here. I'll call this piece number 1. And this is when x goes left. So this is what you'd be given on a problem. We'll call this number 1. I'll call this piece number 2. Now, I'm not sure exactly what the x value is, so I'm going to have to look here closely. It looks like it's counting by ones, and it breaks somewhere around 1.5. That's not very good. So it's not even 1.5. It's somewhere in between. That's just going to be problematic. We're going to skip that one because I don't know what the x value is. If I'm giving the problem, make sure I know what the x value. And so I'm also going to look at this. We'll call this one number 2. The right in behavior. What's happening on the right side? So we'll take a look at these 2. And so this time, as we go farther and farther left, does it appear that the graph is going up? Is it going down, or is it getting really flat?
It's getting flat.
It's getting flat. And so you can kind of look on the y-axis and see that it's getting flat on this line. If you go across, the value it's getting flat on appears to be 6. It appears to be getting flat on this line here, which is y equals 6. If you straighten that out. And so the answer here would be y equals 6. So as the graph goes left forever, it approaches 6. Or as it goes right forever, it approaches 6. If I touch the graph with Desmos, it'll tell me the y values. If you look at the y values, they're getting really close to 6. And especially if I zoomed out more and more, they would get really, really, really close to being exactly 6. See how that's like 6.009 for the y? Over here, it's 5.991. So we're getting really close. If you kept zooming out, 6.002. It's getting so close. So yeah, that was the line. All right, it was getting really close to being 6 exactly. And I don't know how I got off there, but either way, it was supposed to be right there. Okay, now I've got another problem to show you. Here's a little trickier one. This you won't see as much in pre-calculus. This is just kind of prepping you for college and calculus here. You might sometimes have a limit that does not exist. On this one, the left end limit does not exist. This one does not exist. Now the simple answer is, why do you think this limit doesn't exist? So this is saying x goes
it's
and
cut off.
that's right, it cuts off. This graph doesn't continue on. It stops at -5. So this graph does not exist. So sometimes in calculus, you might have more of these where you have limits that don't exist, but in pre-cal, most of our limits are going to exist. So you won't see that very often, but I just want to show you. If the graph cuts off, it doesn't have a left limit like that. It would have a right limit because the graph does move to the right forever. And so we could find this limit of x going to infinity. So you look on your x-axis. As we get bigger and bigger, what's the y's doing? Well, they're staying flat on this line. They're staying flat on the line y equals 6. The y-axis is 6. So that would be the answer to this limit over here. But this limit would not exist. Let's review this. What would you call this point right there and that point right there? What are both of those points?
Maximum.
Those are maximums. Very good. Now, they're not the highest point in the graph, so they would not be absolute, but they are maximums. This point right here, what would you call that point? And this point, for that matter. A minimum. Very good. Those are minimums because they appear at the top of like a valley. So I call these valleys, not a valley. This is like a little hill, another little hill. So those are maximums occur at the top of the hill, minimums occur at the bottom of the valley. And here would be another minimum right in there, it looks like, because the graph curves up a little bit. So that'd be one more minimum. Okay. Now I have a few more things to show you, just kind of to help this get sunk in. So I'll give you an easier problem here. If you see an open circle, does that mean it's continuous, or does that mean it's broken apart if you have an open circle?
Broken apart.
That's broken apart. Do you remember out of the three names, infinite, removable, or jump, which one is just a little open circle like that?
Removable.
Very good. This answer would be removable. This point right here is called a what?
The bottom right, that one.
Yeah.
Minimum.
Minimum, good. And our limits. So I'm now giving you difficulty that you'll get today. You'll need to know that that's a minimum, that it's removable because it was an open circle, and you would have to find this limit. As we're going this direction, which way is X going right here on this arrow?
Upward.
X, the X on the X's. Is the X moving to positive infinity or negative infinity?
Positive infinity.
Okay. And what's Y doing? Is it moving positive or negatively?
Negative.
So the Y's are going down?
Positive infinity?
No, they're going up.
They're going up. So if you were going to write a limit here, you would say it's going Y's, f of X represents Y. Y is going up when X goes right. And then on this side, the left end behavior. As we move left, as this graph moves further and further to the left, what's happening to the Y's? Do they move up or down or flat?
Up.
Up. And so the answer would be positive infinity. That's more the difficulty you'll see today. One more thing, just a reminder. What would you call this break? What's that one called?
Jump.
Jump. You got it. So there's an overview of last lesson and lesson 1-4. I just gave you an overview of both. So if you have any other questions, you can hang on and ask me. But other than that, that's the end of the general overview. I think you're good to go.